There is a question you can explain to a child in about 30 seconds. Pick any positive number. If it is even, cut it in half. If it is odd, multiply it by 3 and add 1. Now do it again with whatever number you got, and again. Keep going. The conjecture says that no matter what number you start with, you will always, eventually, reach 1. That is the entire problem. There is no hidden clause, no fine print, no graduate level abstraction buried under the surface. You could teach this rule to a 10-year-old over breakfast, and they would understand every word of it. The operations involved are multiplication, addition, and division. The kind of arithmetic you learned before you learned to ride a bicycle. And this problem has defeated every mathematician who has ever attempted it. Not most of them. Every single one. For 89 years. The full collective weight of modern mathematics, every technique, every proof strategy, every framework developed and refined over 4 centuries of accumulated genius has been aimed at this question. All of it has failed. Paul Erdos, the most prolific mathematician of the 20th century, a man who published more than 1,500 papers across virtually every branch of the field, looked at this problem and said that mathematics is not yet ready for such problems. That was in the early 1980s. More than 4 decades have passed since, and he has been proven right every single day. Here is the part that very few people are willing to state clearly. There is a serious, well-grounded possibility that the proof does not exist. Not that nobody has found it yet, that it cannot be found, that the system of logic we built to reason about numbers may be structurally incapable of answering this particular question. We will get to that, but first, you need to understand what this problem actually does to numbers, and why mathematicians are afraid of it, and how a question about the number 3 has quietly humiliated an entire discipline. The rules one more time, because the simplicity is the whole point. Take any positive whole number. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Take whatever number you get and do it again. That is it. Those are the only operations. A child could execute them with a pencil and paper. Start with the number 7. 7 is odd, so you multiply by 3, getting 21 and add 1. 22. 22 is even, so you divide by 2. 11. Odd. Multiply by 3 and add 1. 34. Even. 17. Odd. 52. Even. 26. Even 13. Odd. 40. 20. 10. 5. 16. 8. 4. 2. 1. 16 steps. From 7, you bounce around unpredictably. You climb past 50, you drop back to the teens. You spike to 40, you cascade down through the powers of 2, and you hit 1. And then you are stuck. 1 goes to 4, goes to 2, goes back to 1. A loop. Forever. That is supposed to happen for every number, every single positive integer. No exceptions. Try 6. 6. 3. 10. 5. 16. 8. 4. 2. 1. 8 steps. Quick and clean. Try 15. 46. 23. 70. 35. 106. 53. 160. 80. 40. 20. 10. 5. 16. 8. 4. 2. 1. 17 steps. peaking at 160. Already, you can feel it getting more volatile. The sequences do not follow a pattern you can describe. They jump, spike, collapse, spike again, and then surrender to 1. Try 9, 19 steps. Try 19, 20 steps, peaking at only 88. The relationship between starting value and path length is not just unpredictable. It seems almost arbitrary. And then there is the number 27. I have to be honest with you about 27, because this is the number that shifted something in my understanding of the problem. I came across it early in the research, and I assumed it would be a routine example. I was wrong. 27 is the number that made me realize this conjecture is not a puzzle waiting to be solved. It is a signal that something about arithmetic itself is stranger than we thought. The number 25 reaches 1 in 23 steps. Reasonable. 26 gets there in 10. 28 takes 18. These are the neighbors. Now watch what 27 does. 27 is odd. Multiply by 3, add 1. 82, divide by 2, 41, odd, 124, 62, 31. The sequence is climbing. 94, 47, 142, 71, 214, 107, 322, 161, 484, 242, 121. The sequence is past 100 and still going up. 364, 182, 91, 274, 137, 412, 206, 103, 310, 155, 466, 233, 700, 350, 175, 526, 290, 395, 1186, 593, 1780, 890, 445, 1336, 668, 334, 167, 502, 251, 754. I could keep going. The sequence does not stop climbing for 77 steps. At its peak, it reaches 9,232. That is over 341 times the starting value. From 27, a number a kindergartner can count to. The sequence then begins a long, erratic descent, not reaching single-digit territory again until step 103, and finally arriving at 1 after exactly 111 steps. You change the starting number by 1 from 26 to 27, and the journey to 1 goes from 10 steps to 111, from a gentle walk to an expedition that climbs to 9,000 feet. Adjacent integers, neighbors on the number line, and they have almost nothing in common. That is not how well understood mathematical systems behave. When you have a simple, deterministic rule with no randomness, no external input, no choice at any step, and adjacent starting values produce radically different trajectories, you are looking at something that does not fit neatly into existing theory. Mathematicians call these hailstone sequences because the numbers rise and fall like hailstones tumbling inside a thundercloud. Updraft, freeze, fall, updraft again. Each cycle chaotic and unpredictable, until the stone finally crashes to earth Every Collatz sequence crashes to 1. Every single one anyone has ever checked. And nobody can prove it has to. The question of how this problem entered the world is itself unusual. It was not published in a journal. It was not announced at a conference. It was not the result of a research program or a collaboration. A young German mathematician named Lothar Collatz, born in Arnsberg, Westphalia, in 1910, wrote it in a notebook. Collatz had studied at some of the most prestigious institutions in Europe. He entered the University of Greifswald in 1928, then moved through Munich, Göttingen, and Berlin. At Göttingen and Berlin, he attended lectures by some of the greatest mathematicians of the era: David Hilbert, Richard Courant, Richard von Mises, Isai Schur. These were legends. He earned his doctorate from Berlin in 1935 under Alfred Klöser, writing on difference methods for linear differential equations, and completed his habilitation at the Technische Hochschule in Karlsruhe in 1937. It was during this period that the 3n+1 rule appeared in his notebooks. He was playing with function iteration, which means taking a function, applying it to a number, applying it to the result, and watching where it goes. He drew diagrams of the orbits. He tried different rules. Most were uninteresting. One was not. The commonly cited year is 1937, based on Collatz's own statements and oral tradition. But here is the strange thing. He never published it, not in 1937, not in the 40s, not in the 60s. The first formal publication of anything resembling the conjecture did not appear until 1971, when Brian Thwaites described it in an Australian mathematics journal. For over 3 decades, the problem existed purely as something Collatz mentioned to people in conversation. It spread through the mathematical community the way folklore spreads, by word of mouth, through handshakes and hallway conversations and dinner discussions at conferences. The pivotal event was the 1950 International Congress of Mathematicians in Cambridge, Massachusetts. Collatz attended and mentioned his problem to several colleagues. Among them were the Japanese-American mathematician Shizuo Kakutani at Yale, the Polish mathematician Stanislaw Ulam at Los Alamos, and the British geometer H.S.M. Coxeter. Each of them carried it home, and at each institution, the same thing happened. Kakutani later described the phenomenon. He said that for about a month, everyone at Yale worked on the problem, with no result. A similar phenomenon occurred when he mentioned it at the University of Chicago, and then he said the line that has become permanently attached to the conjecture. A joke was made that this problem was part of a conspiracy to slow down mathematical research in the United States. That was a Cold War-era joke. The implication was that the Soviets had planted an unsolvable problem in American academia as a form of intellectual sabotage. It was funny because it felt true. The problem is genuinely infectious. You look at the sequences, you think you see a pattern forming, you think you are one insight away from cracking it open. Then the pattern dissolves, and 3 weeks are gone. By the late 1950s, the conjecture had different names at every institution. The Syracuse problem at Syracuse University, Kakutani's conjecture at Yale, Ulam's problem at Los Alamos, Hass's algorithm at Hamburg, where Collatz had described it to the number theorist Helmut Hasse in 1952. The problem had become mathematical folklore. It belonged to everyone. It could be solved by no one. I personally think there is something almost poetic about a question concerning numbers that cannot be pinned down, spreading uncontrollably through the mathematical world. resisting every attempt to corner it. It behaves exactly like the sequences it describes, rising, falling, appearing to go somewhere, and then not. Which brings us to the obvious first strategy. If you cannot prove the conjecture is true for all numbers, surely you can check enough of them to settle the matter. Computers are fast, numbers are patient. Just start at 1 and work your way up. That is exactly what people have been doing for over 50 years. And the scale of what has been accomplished is staggering in its own right, even though it ultimately proves nothing. The first systematic computational verification dates to 1973, when Richard Dunn at the University of Colorado confirmed the conjecture for all numbers up to approximately 29 million. That was impressive for the era. By today's standards, it is less than a rounding error. Through the 1980s and 90s, the record crept upward. Various researchers pushed the boundary into the billions, then tens of billions, then hundreds of billions. Tomás Oliveira e Silva at the University of Aveiro in Portugal held the record for much of the 2000s, eventually reaching approximately 20 times 2 to the 58th power, which is around 5.76 times 10 to the 18. That took 81 CPU years. A volunteer computing project called Yo-Yo at Home, using distributed computing from about 1,000 volunteers, pushed past 10 to the 20th around 2017. Then, David Barina entered the picture. Barina is a researcher at the Center of Excellence IT for Innovations at Brno University of Technology in the Czech Republic. His project began on September 4th, 2019, and what he has achieved since then needs to be stated plainly so you can feel its weight. His verification has consumed 12,395 CPU years and 159 GPU years of continuous computation running on the Metacentrum computing grid with up to 2,000 CPU cores on Karolina, the Czech Republic's most powerful supercomputer, and on Lumi, which was at the time the most powerful supercomputer in all of Europe. On January 15th, 2025, the project reached its latest milestone. Every positive integer up to 2 to the 71st power has been verified. Every single one reaches 1. 2 to the 71st power is approximately 2.36 times 10 to the 21st. That number has 22 digits. In full, it is roughly 2,361 quadrillion. If you tried to counter this number at 1 integer per second, it would take about 75 trillion years. The universe has existed for approximately 14 billion years. You would need over 5,000 times the current age of the universe. And Barina's algorithms are not brute force. They are elegantly optimized. The key insight is that since numbers are verified in ascending order, you only need to iterate each number until its orbit drops below the starting value. Everything below that has already been checked. On top of this, he uses sieve methods that pre-compute the behavior of numbers based on their lowest k bits. For k equals 34, the sieve eliminates the vast majority of starting values without performing any iteration at all. Additional 3 to the k sieves exploit the fact that numbers congruent to 2 modulo 3 never need to be tested, cutting the search space by another 44%. A crucial 2021 innovation replaced exponentially large lookup tables with linear-sized tables using powers of 3, slashing memory requirements. His GPU implementation processes approximately 220 billion 128-bit numbers per second. That is over 52 times faster than the best CPU code. The total speedup from the first naive implementation to the current optimized GPU version is a factor of 1335. During the run to 2 to the 71st power, the project discovered 5 new path records, numbers whose trajectories reach peaks higher than any smaller starting value. The largest of these new records is 2,589,09599,86,7980,429,759. These are numbers with 19 digits, producing trajectories that reach peaks nobody had seen before. The sequences are still producing novel behavior at the very edge of the verified range. And no, I am not making any of this up. It is published in 2 peer-reviewed papers in the Journal of Supercomputing. The 2021 paper covers the earlier milestone of 2 to the 68th. The 2025 paper covers 2 to the 71st. Barina's code is open source on GitHub. The entire verification is independently reproducible, but none of it is proof. This is the part that is hardest to communicate to people outside mathematics. Checking numbers is not proving a theorem. No finite amount of checking can ever be a proof for a statement about infinitely many numbers. 2.36 sextillion is an incomprehensibly large quantity. It is also an infinitesimally small fraction of the positive integers. The integers go on forever. The conjecture says every single one reaches 1. Barina has checked less than 1 in a trillion of them. The history of mathematics includes multiple examples of conjectures that were verified computationally for staggering ranges, before turning out to be wrong. The Collatz Conjecture, proposed in 1919, claimed that the majority of integers up to any given value have an odd number of prime factors when counted with multiplicity. It was verified for every number up to roughly 906 million. Then counterexamples were discovered. The conjecture is false. The Mertens conjecture about partial sums of the Mobius function was widely believed true based on decades of computational evidence. In 1985, Andrew Odlyzko and Herman Terriele proved it false. The estimated first counterexample is larger than 10 to the power of 10 to the power of 40. That is a number with more digits than there are atoms in the observable universe. No computer will ever reach it by direct search. And the conjecture was still wrong. So when someone says the Collatz conjecture is probably true because it has been checked for sextillions of numbers, you need to understand what that sentence actually means. It means nothing has gone wrong yet. That is all. The search space is infinite. We have scratched its surface with our fingernails. And this is where Lothar Collatz's own biography becomes haunting. Because the man who wrote the question in a notebook in 1937 lived another 53 years. He watched it spread across the globe. He watched it resist every approach. He watched careers bend and sometimes break against it. And he died without seeing it answered. His career was far broader than this. One problem, he held a professorship at the University of Hamburg for over 25 years and founded their Institute of Applied Mathematics in 1953. His contributions to numerical analysis were substantial. The Collatz-Wieland formula for Perron-Frobenius eigenvalues remains standard material. In 1957, he and Ulrich Sinogowitz published a paper that essentially founded the field of spectral graph theory. MathSciNet records 238 publications under his name. He received honorary degrees from 6 universities on 3 continents and was elected to the German Academy of Sciences, Leopoldina. During the war, he served as chief ballistician on the V-2 rocket program at Darmstadt. He survived the devastating Allied bombing of that city on September 11, 1944. He was later located and interrogated by British intelligence in June of 1945. Colleagues described him as truly wonderful, modest in his behavior, ever amiable and helpful. His biography at MacTutor contains a quiet sentence that I think about often. It says that in many ways, it might seem a pity that a mathematician who has produced so much important and fundamental work should be most remembered for a novelty. He died on September 26, 1990, of a heart attack in Varna, Bulgaria. He was attending a mathematics conference. Working until the end, his novelty was 53 years old and unsolved. It has now been 89 years. The conferences continue. The conjecture persists, and every tool that has been aimed at it has shattered on impact. So computation has given us certainty about the first 2.36 sextillion numbers. But certainty about a finite range is not proof. Therefore, mathematicians turn to theory. Surely, the abstract tools of modern mathematics, the same machinery that cracked Fermat's last theorem after 350 years, that resolved the Poincaré conjecture, that mapped the distribution of prime numbers with astonishing precision, could handle a question built from nothing more than multiplication, addition, and division by 2. They could not, and the pattern of how they failed is the most revealing part of the entire story. I spent a long time going through the published literature on failed proof attempts, longer than was probably healthy, and what struck me was not that any individual technique broke down. That happens in mathematics all the time. Hard problems resist easy solutions. What struck me was that every approach, regardless of which branch of mathematics it came from, regardless of which century it was developed in, hits the exact same wall. And the wall is always in the same place. It is the +1. Think about what the Collatz function actually does at each step when it encounters an odd number. First, it multiplies by 3. Multiplication is an operation that lives in the multiplicative world of number theory. If you know the prime factorization of n, you know the prime factorization of 3n. It is just the same primes with an extra factor of 3. Multiplicative structure is fully preserved. Divisibility relationships stay intact. The algebraic information you have about the number survives the multiplication completely. Then you add 1, and everything dies. If you know the complete prime factorization of n, you know almost nothing useful about the factorization of n plus 1. 100 is 2 squared times 5 squared. 101 is prime. 102 is 2 times 3 times 17. Completely different structures. Addition and multiplication are like 2 languages that share no vocabulary. The Collatz function forces you to switch between them at every odd step. Multiply by 3, you are in the multiplicative world. Add 1, you crash into the additive world. Divide by 2, you stumble back into multiplicative territory. Then you hit another odd number, and the whole violent cycle repeats. This is not a metaphor. It is a precise description of why every technique fails. Every branch of mathematics that has been applied to this problem is optimized for one of these 2 worlds but not both. Modular arithmetic was the first systematic theoretical approach. The idea is simple. You study numbers not by their exact values, but by their remainders when divided by some fixed number. And it yields results up to a point. You can prove that any counterexample to the Collatz conjecture, if one exists, must be odd. It must be congruent to 3 modulo 4. At higher moduli, increasingly restrictive conditions hold. These sieves can eliminate large classes of numbers as potential counterexamples. But the number of surviving residue classes, the ones you cannot eliminate, grows exponentially as the modulus increases. You are patching holes in a net where new holes open faster than you can close the old ones. No finite sieve, no matter how large, can rule out all possibilities. The survivors are always out there, uncountably many of them, resisting classification. P-adic analysis found something genuinely beautiful and genuinely useless. The Collatz map extends naturally to a number system called the 2-adic integers, which is organized entirely around divisibility by 2 rather than around size. In this 2-adic world, the Collatz function is continuous. It preserves measure. It is ergodic, which means that over time, orbits visit every part of the space with uniform frequency. Every conceivable infinite sequence of even and odd steps, every possible binary pattern of ups and downs, corresponds to exactly one 2-adic starting value. The theory is elegant, complete, and perfectly understood. But the positive integers, the numbers we actually care about, the numbers the conjecture is about, form a set of measures 0 inside the 2-adic integers. They are invisible, completely invisible. Proving something about the 2-adic Collatz map tells you nothing about the positive integers. It is like having a flawless satellite map of an entire continent and discovering that the one village you need to find does not appear at any zoom level because it is too small to register. Maxwell Siegel, in a 2024 paper, tried to extend this to what he called P, Q-adic analysis, working simultaneously with the 2-adic and 3-adic integers to capture the inherently 2' structure of the Collatz map. The framework is novel and interesting. It has not produced a proof. Dynamical systems theory, the standard mathematical framework for studying how systems evolve over time, was designed for continuous systems with smooth structure. The Collatz map operates on the positive integers, which are discrete, isolated points with no continuity between them. There is no smooth surface to study, no curvature to measure, and critically, there is no Lyapunov function, which is the standard tool for proving a dynamical system converges. A Lyapunov function is a quantity that decreases along every trajectory, guaranteeing eventual convergence. For the Collatz map, nobody has found one. Nobody has even found a plausible candidate. The sequences bounce so erratically that no single measure of progress consistently decreases from step to step. Analytic methods developed by Berg and Erdos in the mid-1990s took an entirely different approach, reformulating the conjecture as a question about holomorphic functions on the complex unit disk. They proved something remarkable. The Collatz conjecture is equivalent to a specific space of analytic solutions being two-dimensional. If you could characterize the solutions to a particular functional equation on the unit disk, you could prove or disprove the conjecture. But the functional equations involve composition with z raised to the 2/3 power, which creates branching and multi-valued behavior. and the unit circle turns out to be a natural boundary. A natural boundary means the function cannot be analytically continued past it. The mathematics literally runs out of space. You can work inside the unit disk and you can work on the unit disk, but you cannot push through to the other side. The proof, if it exists by this route, requires information from a region the theory cannot reach. Every single one of these approaches reveals something about the problem. Every single one breaks at the same point. The point where you need to say something definitive about one specific orbit of one specific number. Not about average behavior. Not about behavior in some abstract extension of the integers. This number, this trajectory, does it reach one? The man who has mapped the landscape of these failures more thoroughly than anyone is Jeffrey Lagarias at the University of Michigan. He first encountered the 3n+1 problem in 1967 as a high school student working at the National Bureau of Standards. He earned his PhD in analytic number theory at MIT in 1974 under Harold Stark. He worked at AT&T Bell Laboratories, then at Maryland and Rutgers, before joining Michigan. And through all of it, the Collatz Conjecture has been there. His 1985 paper in the American Mathematical Monthly, titled The 3x+1 Problem and Its Generalizations, is the foundational survey. It is the most cited reference on the conjecture. His 2010 book, published by the American Mathematical Society, The Ultimate Challenge, is the definitive treatment, containing surveys, research papers, reprints of 6 seminal early works, and an annotated bibliography of over 200 entries spanning decades of work. Lagarias has compiled the most comprehensive scholarly accounting of the problem that exists. And his diagnosis of why the problem is intractable is, I believe, the single most important paragraph ever written about the Collatz conjecture. He wrote that empirical evidence indicates the 3x+1 function retains pseudo-randomness on its initial iterates until those iterates enter a periodic orbit, and that this pseudo-randomness supports the conjecture while simultaneously depriving us of any obvious mechanism to prove it, because mathematical arguments exploit the existence of structure rather than its absence. That deserves a moment. The conjecture may be true because the sequences behave like random processes. The odd steps and even steps mix together in patterns that have no exploitable regularity. And proof by its nature requires finding a pattern, a structure, an invariant, something that persists across all cases and allows you to make a universal statement. If the truth of the conjecture depends on the absence of structure, then proving it requires proving a negative about randomness, which is exactly the kind of thing mathematics is worst at. Lagarias called the Collatz conjecture an extraordinarily difficult problem, completely out of reach of present-day mathematics. In 2019, speaking to Quantum magazine, he said it was really dangerous and that people become obsessed with it, and it really is impossible. Then he added, and I think this is the most quietly devastating thing a mathematician has ever said about an open problem, that he now knows lots more about the problem than he did in 1985. And he would still say it is impossible. That is not frustration. That is a clinical assessment from a man who has studied the problem for close to 60 years. And this is where Paul Erdos enters properly, because his role in the story is not just the famous quote. It is the diagnosis that preceded the quote. Erdos was born in Budapest in 1913. Both his parents were mathematics teachers. He published his first paper at age 17 and received his doctorate at 21. from the University of Budapest. And then he did something that nobody had done before or has done since. He became a full-time itinerant mathematician. He owned essentially nothing. No house, no car, no permanent address, no steady job. He traveled continuously for over 60 years, living out of a single battered suitcase and a plastic bag, showing up at colleagues' doorsteps and announcing that his brain was open. He would work for a few days or weeks at one institution, collaborate furiously, produce papers at a rate that nobody could match, and move on. He slept little. He fueled himself with espresso and amphetamines, primarily Benzedrine and Ritalin, which he took daily for much of his adult life. When his friend Ron Graham bet him $500 that he could not abstain from stimulants for 30 days, Erdos won the bet. And then he told Graham, with the blunt honesty that was his defining characteristic, that during the month he had not gotten any work done. "You have set mathematics back a month," he said. He published approximately 1,500 papers with more than 500 co-authors, creating an entire subculture within mathematics organized around collaboration with him. The Erdos number, which measures how many collaborative links separate you from him, became a badge of honor. Having Erdos number 1 means you wrote a paper directly with him. There are over 500 such people. Having Erdos number 2 means you collaborated with someone who collaborated with him. The network extends outward into the tens of thousands. He spoke of the book. The book was an imagined volume where God kept the most elegant, most beautiful proof of every theorem. "You don't have to believe in God," Erdos would say, "but you should believe in the book." The highest compliment he could give a proof was to say it was from the book. He offered $500 for a proof or disproof of the Collatz Conjecture. That placed it in the upper middle range of his personal bounty system, which ran from $25 for routine problems to $10,000 for the most difficult conjectures he knew of. He never published a research paper on the Collatz Conjecture himself. His contribution was diagnostic. He recognized that the problem lay outside the boundaries of what existing mathematics could handle. He said so plainly and moved on. Mathematics is not yet ready for such problems. A variant of the quote, attributed to approximately 1983, reads, "Mathematics may not be ready for such problems." The first printed record appears in Lagarias' 1985 paper. Either way, it has been correct every day for over 40 years. Erdos died on September 20th, 1996, in Warsaw, Poland. He was 83 years old. He was attending a mathematics conference. Like Collatz, he died doing mathematics. Like Collatz, his assessment of the problem outlived him. The $500 remains uncollected. The reason every approach fails has a deeper explanation than insufficient cleverness, and the nature of that explanation connects to something about mathematics itself that most practitioners would rather not discuss publicly. But before we get there, something happened in 2019 that needs to be understood, because it is simultaneously the closest anyone has ever gotten and the clearest measurement of how far away a solution remains. In September of that year, Terence Tao posted a paper to the Arxiv. The title contains 2 words that you should pay attention to. Almost all orbits of the Collatz map attain almost bounded values. 2 almosts, not all. Almost all, not bounded. Almost bounded. The paper was published in Forum of Mathematics, Pi, in May of 2022. It is the strongest theoretical result on the Collatz Conjecture in the history of the problem. Tao is routinely described as the greatest living mathematician. Born in Adelaide, Australia, in 1975, he was teaching other children to count by age 2. Taking calculus at 7, he scored 760 on the Math SAT at 8 years old. At 13, he won a gold medal at the International Mathematical Olympiad, the youngest gold medalist in the competition's history. He completed his bachelor's, honors and masters at Flinders University by 16, PhD from Princeton at 20, under Elias Stein, full professor at UCLA at 24, the youngest in the university's history. Fields Medal at 31 for contributions across harmonic analysis, partial differential equations, combinatorics, and number theory. His Green-Tau theorem, proving that the prime numbers contain arithmetic progressions of arbitrary length, is one of the landmark results of 21st century mathematics. And there is a detail that connects him to our story. At age 10, Tau met Paul Erdos. Erdos was visiting Adelaide, and as he often did, he spent time with mathematically gifted children. He called them epsilons, after the mathematical symbol for a very small quantity. Young Terry Tau was one of his epsilons. 3 decades later, he took on the problem Erdos said mathematics was not ready for. What Tau actually proved requires a moment of patience. Take any function f of n that goes to infinity as n goes to infinity. Any function at all. It can grow as slowly as you like, slower than the logarithm, slower than the log of the log, slower than any function you can write down, as long as it eventually, somewhere, goes to infinity. Tau proved that the minimum value reached by the Collatz orbit starting from n is less than f of n for almost all positive integers n in the sense of logarithmic density. Logarithmic density means you weight each integer n by 1 over n. Instead of counting uniformly, a set has logarithmic density 1 if it captures almost all numbers in this weighted sense. It is weaker than ordinary density. A set can have logarithmic density 1 without having ordinary density 1. The previous best result was due to Ivan Korek in 1994, who proved that orbits drop below a fixed power of the starting value for almost all n in the stronger sense of natural density. Tau replaced the power bound with an arbitrarily slowly growing function. The improvement is enormous, but Tau was explicitly clear about the gap. He told Quantum magazine that you can get as close as you want to the Collatz conjecture, but it is still out of reach. He said, any proof of the full conjecture would likely depend on a fundamentally different approach, not an extension of his methods, not a refinement, something qualitatively new. The paper's origin has become legendary in mathematical circles. Tau disciplines himself to spend only a few days per year on hopeless problems. The rest of his time goes to problems where progress is genuinely achievable. In August 2019, an anonymous commenter on his 2011 blog post about the Collatz conjecture left a suggestion. Try proving the result for almost all numbers rather than all numbers. Tau did not reply to the comment, but, as he later told interviewers, it got him thinking about the problem again. Within weeks, the breakthrough paper appeared. Matt Mullenweg, the co-founder of WordPress, later highlighted this as a particularly vivid example of blog comments' unexpected power. An anonymous stranger posting on a mathematics blog nudged the greatest mathematician alive toward the strongest result in the history of the problem. That is either inspiring or terrifying, depending on how you look at it. I have been obsessed with the gap between Tau's result and a foolproof since I first understood it. The gap cannot be closed by working harder or having more time. What separates almost all from all is a chasm between two fundamentally different types of mathematical claim. Almost all numbers versus all numbers. Statistical truth versus universal truth. And in this context, the distance between those two things is infinite. Proving that 99.999% of numbers behave a certain way gives you exactly zero information about whether the remaining numbers do too. The conjecture demands all. Tau delivered almost all, and almost all is not all. You may have heard that Terence Tao proved the Collatz Conjecture. He did not. What he proved is that the problem is approachable from a probabilistic direction, and that the probabilistic approach hits a hard ceiling. The ceiling is the word all. There are 4 unclaimed prizes for resolving the conjecture. Erdos is $500, Coxeter's £50, Brian Thwaites offered £1,000 in the Mathematical Gazette in 1996. In an article where he cheerfully noted that some will attribute his continuing interest in such apparently elementary mathematics to well-advanced senility. And in July of 2021, a Japanese company called Bakuage announced 120 million yen, approximately $1,085,000 US, requiring publication in a MathSci.net listed journal and a 2-year waiting period for community verification. The total exceeds $1.6 million. All of it waiting, none of it close to being claimed. The mathematical profession treats this problem with something closer to fear than fascination. Quanta magazine described it as dangerous, a siren song. Fall under its trance, and you may never do meaningful work again. Scientific American published similar warnings. Lagarias himself called it impossible. Tao described the occupational hazard of becoming fixated on problems that are way beyond anyone's ability to touch. The internet is, as Quanta put it, awash in unfounded amateur proofs. Even professionals are not immune. Gerhard Opfer, a mathematician at Hamburg, who had been Collatz's own doctoral student in the 1960s, submitted a claimed proof in 2011. It did not survive scrutiny. I think the most underrated aspect of this entire story is the profession's collective response. The posture is not scientific curiosity. It is avoidance. And the avoidance itself is data. When some of the smartest people on the planet spend 60 years studying a problem, and their conclusion is, do not look at this, that is not a confession of failure. It is a detection. They are detecting something about the boundary of mathematical knowledge itself. The career danger angle is not an exaggeration, and it is not folklore. It is a specific, documented pattern. The internet is full of claimed proofs of the Collatz Conjecture. Arxiv has them. ResearchGate has them. Personal websites have them. A 2025 paper in a Taylor and Francis journal included an acknowledgement that it was prepared with the assistance of ChatGPT, which tells you something about the current state of Collatz proof attempts. None of these claimed proofs have been accepted by the mathematical community. Every single one has either contained a gap, relied on an unverified assumption, or simply not constituted a valid proof. Gerhard Opfer at the University of Hamburg who had been a doctoral student of Collatz himself in the 1960s, submitted acclaimed proof in 2011. Opfer was not an amateur. He was a professional mathematician with a legitimate academic career who had a direct personal connection to the problem's creator. His proof did not survive peer review. If a student of Collatz cannot crack it, the problem is not about cleverness. It is about something else entirely. The Soviet conspiracy joke, the one Kakutani attributed to his visits to Yale and Chicago in the 1950s, has survived for over 60 years because it captures a real dynamic. The problem is addictive in a specific and dangerous way. The addiction does not work the way hard problems normally work, where you feel like progress is possible if you just think harder. The Collatz Conjecture hooks you the way a slot machine hooks you. It gives you periodic small rewards, moments where you think you see a pattern, moments where a new approach seems to illuminate something, and then it takes them all away. The intermittent reinforcement is exactly what makes it psychologically toxic for working mathematicians. I've been thinking about this problem on and off for months now, and I can feel the pull myself. Every time I think I have moved on, some detail pulls me back. The fact that 27 takes 111 steps while its neighbors take 10 and 18. The fact that Barina found new path records at 22-digit numbers. The fact that Dow said any foolproof would require something fundamentally new. Each of these facts feels like it should point somewhere, like there should be a thread connecting them. And then you pull the thread and it leads nowhere. Or worse, it leads you in a circle and you have lost another evening. Tao described this explicitly. He called it an occupational hazard, getting obsessed with famous problems that are way beyond anyone's ability to touch. His solution is disciplined restraint. He limits himself to a few days per year on what he calls hopeless problems. The rest of the time, he works on problems where progress is actually possible. That discipline, the ability to engage with the problem and then walk away, is itself unusual. Very few people who encounter the Collatz conjecture have it. There is a second, deeper reason the mathematical community avoids this problem, beyond the career risk. And this reason is rarely stated out loud. Working on the Collatz conjecture means confronting the possibility that mathematics has permanent limitations, not temporary limitations that will be overcome with better tools. Permanent ones. Hard boundaries. And most working mathematicians do not want to think about that. They have built their careers on the assumption that sufficiently hard work applied to sufficiently well-posed problems will eventually yield answers. The Collatz conjecture challenges that assumption in a way that no other problem quite does, because it is so simple. If this question, this child's arithmetic exercise, turns out to be beyond the reach of proof, then what does that say about the enterprise of mathematics itself? This is not an abstract philosophical concern. It connects to specific, proven theorems about the nature of mathematical reasoning. And to understand those theorems and what they imply for the Collatz conjecture, you first need to understand what makes the number 3 so special. Because when you take that 3 out and replace it with something else, the whole system changes character, and the nature of the change tells you exactly where the difficulty lives. And what they are detecting has to do with the number 3 itself. Because when you change that single number, when you swap the 3 for a 5 or a 7, everything changes. And what that reveals about 3 is not just mathematically interesting, it is unsettling. The heuristic argument for why the Collatz conjecture should be true runs like this. When the sequence hits an odd number, you compute 3n plus 1, which always produces an even number. You then divide by 2, but on average, you divide by 2 more than once, because about half the time, the result of the first division is still even. Working through the statistics carefully, the average effective multiplier per complete odd step turns out to be approximately 3/4. And since 3/4 is less than 1, the orbit should shrink on average, drifting gradually downward toward 1, like a random walk with a slight downhill bias. That argument is intuitive, it is elegant, and it is not a proof. The critical flaw is the word average. The heuristic assumes that each step is independent of the previous ones, that the probability of the next step being a division versus a multiplication is unaffected by the current value's history. This assumption is false. The divisibility properties of 3m plus 1 are correlated with n in ways the heuristic ignores. Individual trajectories can and do deviate wildly from the average. 27 takes 111 steps to reach 1. Its neighbors take 10 and 18. The average says nothing about specific cases, and the conjecture is a statement about every specific case. But the heuristic reveals something profound when you vary the multiplier. Change 3 to 5. Now the rule is, if n is odd, compute 5n plus 1, then divide by 2. The effective average multiplier per odd step becomes approximately 5/4. 5/4 is greater than 1. The heuristic predicts that sequences should grow on average rather than shrink. And this time the heuristic is vindicated. The 5n plus 1 problem has counterexamples. Real, verified, undeniable counterexamples. Starting from 13, the sequence enters a cycle of 10 elements that never reaches 1. 13, 66, 33, 166, 83, 416, 208, 104, 52, 26, and back to 13. A closed loop, permanently cycling. Starting from 17, you get another cycle of 10 elements. Starting from 7, the sequence appears to diverge to infinity entirely. The orbit growing without bound, no cycle, no convergence, just unbounded growth. The 5n plus 1 conjecture is false, decisively and provably. That is not a small detail. Think about what it means. You replace the 3 with a 5, you keep everything else identical, and the fundamental character of the system flips from apparent universal convergence to definite divergence and cycling. A single change in one number, from 3 to 5, and the whole structure collapses. The 5n plus 1 world is one where the conjecture is false, provably, undeniably false. Numbers get trapped in loops. Numbers fly off to infinity. The behavior that 3n plus 1 supposedly prevents is alive and well 2 integers away. And this is something I keep coming back to. The distance between 3 and 5 is just 2. 2 integers apart on the number line. One of them produces a system that has resisted proof for almost 90 years and may be unprovable. The other produces a system that is trivially falsifiable in seconds. Whatever property of the number 3 makes the conjecture work, it is precise enough that 5 does not share it. The mechanism, if there is one, operates with surgical specificity. David Barina himself studied a 7n plus or minus 1 variant in 2024. The rule was modified so that the sign of the 1 is chosen to guarantee the result is always divisible by 4, ensuring at least 2 halvings per odd step. This variant, where the effective multiplier works out to less than 1 because of the extra guaranteed halvings, appears to converge for all starting values tested up to 10 to the 15th power. But the stopping times are dramatically longer than for 3n plus 1. Below 1000, the longest 3n plus 1 stopping time is 178 steps. For the 7n plus or minus 1 variant, it exceeds 1000. And the 3n minus 1 problem, which is mathematically equivalent to running the standard 3n plus 1 rule on negative integers, is its own kind of disturbing. There are 3 known non-trivial cycles, not one cycle like the positive case. 3 separate cycles, a 2-element cycle containing -1 and -2, a 5-element cycle, and an 18-element cycle. The existence of multiple cycles for 3n-1, and apparently only the single trivial cycle for 3n plus 1, is itself unexplained. Any proof of the Collatz conjecture must invoke a property that distinguishes +1 from -1. Nobody has identified what that property is. A 2020 paper on generalized Qn plus 1 maps confirmed the picture quantitatively. For Q equal to 3, the probabilistic model predicts convergence for all starting values. For Q equal to 5 or greater, it predicts divergence for almost all starting values. 3 is the critical value, the tipping point, the phase transition. Let me say that more plainly, because I think this is the core of the whole story, and it tends to get buried under the technical details. The number 3 generates sequences that are right on the edge. The average shrinkage per odd step is just barely less than 1. The system just barely tends to decrease, and that razor-thin margin, that tiny statistical lean toward convergence, appears to be enough to drag every trajectory down to 1 eventually. But the margin is so thin, so delicate, that proving it holds universally for every single starting value, without exception, requires a kind of control over the interplay between addition and multiplication that no mathematical framework can currently deliver. The problem is not hard because 3 is a bad choice. The problem is hard because 3 is the precise boundary where deterministic arithmetic starts producing behavior that is indistinguishable from randomness. And now we have to go to the place that most popular accounts of this conjecture never go, because the connection between the Collatz conjecture and randomness is not just a metaphor. There is a formal result proven in 1972 that makes the connection precise, and its implications are deeply uncomfortable. John Horton Conway was one of the most creative mathematicians of the 20th century. He invented the game of life. He classified the sporadic groups. He made fundamental contributions to group theory, number theory, and combinatorial game theory. In 1972, he published a short paper called Unpredictable Iterations. It was only 4 pages long. What it proved is, I believe, one of the most underappreciated results in all of modern mathematics. Conway considered generalized Collatz functions. These are piecewise affine maps, where for each possible remainder when dividing by some fixed modulus p, the function applies a different linear rule. The standard Collatz function is a special case with p equal to 2, 1 rule for even numbers and 1 for odd. Conway's generalization allows p to be any integer and the rules to be any affine functions. He proved that these generalized functions can simulate Turing machines. A Turing machine is the mathematical formalization of a general-purpose computer. It is the theoretical model that underlies every piece of computation that has ever been performed, from pocket calculators to supercomputers to the device you are using right now. Any computation that can be performed by any machine, real or theoretical, can be modeled by a Turing machine. This is the Church-Turing thesis, and it is one of the foundational principles of computer science. The halting problem for Turing machines, the question of whether a given program will eventually stop or will run forever, was proved undecidable by Alan Turing in 1936. There is no algorithm, no procedure, no finite method that can correctly answer this question for every possible program. It is not just that we have not found such a method, it cannot exist. This is a proven impossibility. Conway's result means that asking whether a generalized Collatz function always reaches 1 is at least as hard as the halting problem. Since the halting problem is undecidable, the generalized Collatz problem is undecidable. No master algorithm can look at an arbitrary Collatz-type function and determine whether all orbits converge. Conway went further. In 1987, he created FRATRN, a programming language of breathtaking minimalism. A Fractran program is nothing more than an ordered list of fractions. Computation proceeds by taking a positive integer, scanning the list from left to right, multiplying by the first fraction that produces an integer result, and repeating. That is the entire language. There are no variables, no conditionals, no loops, no data structures, just fractions and multiplication. And Fractran is Turing complete. Every computation that any computer can perform, from sorting algorithms to neural networks, can be expressed as a Fractran program. And Fractran programs are special cases of Collatz-like iteration functions. The 3n+1 map is not itself a Fractran program because it includes the +1, making it affine rather than purely multiplicative. But it lives in the same family. It is a near relative of functions that can compute anything. In 2007, Stuart Kurtz and Janos Simon at the University of Chicago proved something stronger. They showed that the universally quantified form of the generalized Collatz problem, given a function g, does every positive integer eventually reach 1 under iteration of g, is pi20 complete in the arithmetical hierarchy. If you are not familiar with the arithmetical hierarchy, the relevant point is this. The first level contains problems that are merely undecidable. The second level, where pi20 sits, contains problems that are undecidable, even relative to an oracle that solves all first-level undecidable problems. The general Collatz problem is not just hard. It is hard in a way that transcends ordinary hardness. And then, in 2024, researchers discovered a 6-state Turing machine whose halting behavior depends on a Collatz-like iteration problem. This ties the conjecture directly to the busy beaver function, BB of n, which is the maximum number of steps an n-state Turing machine can run before halting. The busy beaver function grows faster than any computable function. It is, in a precise sense, the fastest growing function in all of mathematics. If we knew the exact value of BB of 15, we could settle a related conjecture of Erdos about Collatz-type sequences. All of this leads to a question that hovers over the entire subject and that very few popular accounts of the Collatz conjecture are willing to ask directly. Is the original 3n+1 conjecture, the one Collatz wrote in his notebook in 1937, the one about whether every positive integer reaches 1. Is that specific conjecture undecidable? Nobody knows. Conway's result applies to the general class, not to the specific instance. The distinction matters. The halting problem is undecidable in general, but you can determine halting for many individual programs. A program that counts to 10 and stops obviously halts. A program that loops forever obviously does not. Undecidability is about the class of all programs, not about each individual program. So the 3n+1 conjecture might be provable. Maybe the right framework, the one Tao says, would need to be fundamentally new, exists, and is waiting to be discovered. Maybe the proof is short and elegant. Maybe it is long and technical. Maybe it uses mathematics that has not been invented yet. But there is another possibility, and I think it is the one that matters most. The one that gives this whole story its real weight. If the Collatz conjecture is true but independent of the standard axioms of mathematics, if it is a sentence in the language of arithmetic that is true in the natural numbers but cannot be derived from any standard set of axioms, then we would be looking at something that has no clean parallel in the public understanding of how mathematics works. We would have a statement about numbers that a child can formulate that uses only multiplication, addition, and division. That can be verified for any specific number by a calculator. That has been checked for every integer up to a 22-digit ceiling that the greatest mathematician alive has proven arbitrarily close to. And that is permanently and forever beyond the reach of formal proof. Not because we lack talent, not because we need more time, because the rules of logical deduction, the axioms and inference rules that mathematics runs on, do not contain enough information to settle this particular question. Kurt Gödel proved in 1931 that any consistent formal system powerful enough to describe basic arithmetic contains true statements that are unprovable within that system. The first incompleteness theorem. We have known for nearly a century that these statements exist. The question has always been whether any statement that mathematicians actually care about turns out to be one of them. The Collatz conjecture has exactly the profile you would expect from such a statement. It is about the natural numbers. It involves the interaction of addition and multiplication, the precise domain where Gödel's theorems apply. Its behavior appears random, blocking proof by structural analysis. Its generalized form is undecidable. Lagarias wrote that Conway's undecidability result indicates the 3x+1 problem could be close to the unsolvability threshold. He added that it is currently unknown whether the problem is itself undecidable, and that no method is currently known to approach the question. Close to the unsolvability threshold. That is Lagarias, the man who has spent 60 years on this problem, describing its position in the landscape of mathematical knowability. Not unsolvable, not solvable, close to the threshold. If you find that unsatisfying, that ambiguity, that permanent maybe, I understand. We are trained to expect answers. We are trained, especially in mathematics, to believe that every well-posed question has a determinate answer that can, in principle, be found. The Collatz conjecture may be the simplest and most vivid counterexample to that belief. Lothar Collatz died at a mathematics conference in Varna in 1990. Paul Erdos died at a mathematics conference in Warsaw in 1996, both of them working until the end. both of them gone before the question was resolved. It has now been 89 years since the conjecture was written in a notebook, and 60 years since Lagarias first encountered it as a teenager. He has spent his entire adult life with this problem. He calls it impossible. Terence Tao met Erdos when he was 10 years old, one of Erdos's epsilons. 30 years later, he proved that almost all orbits get arbitrarily close to 1 in a weakened density sense, using a fundamentally novel probabilistic approach. Then he said, with the plain-spoken honesty that is his hallmark, that the full conjecture requires something entirely different, something nobody has thought of. There are $1.6 million in unclaimed prizes, 12,000 CPU years of computation that proved nothing, 5 new path records at 22-digit numbers, meaning the sequences are still surprising us, 3 known non-trivial cycles for 3n-1, and apparently none for 3n+1, and nobody can explain the difference. A generalized version, proven undecidable, a specific version sitting close to the unsolvability threshold, and a mathematical community that treats the whole subject with the wariness of people who have watched it consume careers. The calculations have been checked. 3 times any odd number plus 1. Divide by 2. Every number humanity has ever tested reaches 1. Every single one, from 7 in 16 steps, from 27 in 111, from 871 in 178, from numbers with 22 digits that required the most powerful computers in Europe to verify. They all reach 1. The rule is simple enough for a child. It has defeated every tool ever aimed at it. And the hardest possibility of all is not that the problem is too difficult. It is that the most reliable system of knowledge humanity has ever built, the one we trust more than physics, more than chemistry, more than any empirical science, the system built entirely on pure logic and deduction, contains permanent blind spots, places where truth exists but proof cannot follow. And a 10-year-old's arithmetic problem about the number 3, about the simplest operations you will ever learn, has found 1. The number 27 takes 111 steps. It climbs to 9,232. It falls. It reaches 1. You can verify every step. You can watch it happen. You just cannot prove it had to.